Welcome to a brand new chapter of Circuit Chats. You followed electrons, jumped band gaps, and mastered the p-n junction. Now it's time to ask the big question. So what? So what? Yes, so what? What can we actually do with a diode? So in this series, we're going to talk about diode applications. In the next few slides, we'll explore how the humble diode becomes part of a power supply, signal control, digital logic, light emission circuits, and even solar power. So from theory to technology, where it's protecting your circuits, converting AC to DC, or lighting up an LED, diodes are everywhere. And now that you understand how they work, it's time to see what they can do. As we step into diode applications, we're going to simplify things, starting with a helpful shortcut, the ideal diode model. So what is the ideal diode model? Well, it's not perfect, but it's fast. The ideal model is the least accurate way to describe a diode's behavior, but it's good enough for troubleshooting or quick predictions. Here's what the ideal model assumes. Forward bias acts like a closed switch. So voltage drop across the diode, 0 volts, right? So V sub F is equal to 0 volts. Current flows freely like a wire. Think of a diode as closed, right? So current moves through as long as it's forward biased. When it's reverse biased, acts like an open switch. So no current flows. So reverse current, or I sub R, is equal to 0 amps. Voltage across the diode equals the applied bias, which is V sub R is equal to V sub bias. And it behaves like an open switch, so completely blocking out the circuit. The equations in the model, V sub F is equal to 0 volts. I sub F is equal to V bias divided by the resistance, the limit resistance. I sub R is equal to 0 amps. V sub R is equal to V bias. And that's it. That's simple, right? Why are we going to use this? Well, this ideal model helps engineers quickly tell if a diode is working or not, and it's great for troubleshooting, lab simulations, learning fundamentals, basic stuff like that. So a recap here will be looking at the diagram. In forward bias, current flows freely. In reverse bias, the path is completely blocked. So no threshold voltage, no internal resistance, just on or off. Hey, listeners, now that we've covered the ideal diode model, let's put it to work. In this episode, we've solved a basic circuit step by step, and you'll see just how easy ideal assumptions can make things. So here's the setup. This is what we're looking at. We have a 5-volt power supply, a 1 kilo ohm resistor, a diode wired in forward bias. We're using the ideal model. So if you can remember that forward bias diode equals a closed switch, the voltage drop across the diode, V sub F is equal to 0 volts. And what are we solving? So we need to calculate the voltage across the diode, voltage across the resistor, current through the resistor. So step one, voltage across the diode. So since the diode is forward biased and we're using the ideal model, right, V sub F, it's going to be 0 volts. Step two, voltage across the resistor. So total voltage is 5 volts. With the diode drop at 0, all of it appears across the resistor. So voltage across the resistor would be 5 volts minus 0 volts, which will equal 5 volts. And now step 3, current through the resistor. So we use Ohm's law to solve for this. I is equal to V divided by R, or 5 volts divided by 1 kilo ohm. That's going to equal 5 milliamps. So in summary, to recap, voltage across the diode is 0 volts. Voltage across the resistor is 5 volts. And current through the system, through the circuit, is 5 milliamps. And this is the power of the ideal model. Quick checks, clear answers, and easy math. Okay, in our last episode, we worked with the ideal diode model. Quick, clean, and close enough for many situations, but if you want more realistic results, it's time to level up to the practical model. So what is the practical model? It's still simplified, but more accurate. This model introduces something we've mentioned before, the barrier potential, the voltage drop across a real diode when it's actually conducting, and the assumptions change now. So in the practical model, the forward voltage, V sub F, isn't 0 anymore. It's about 0.7 volts for silicon diodes. That voltage drop is always present when the diode is forward biased. So the current becomes I sub F is equal to voltage bias minus 0.7 volts divided by the resistor, the limit resistor resistance. Now, reverse bias still blocks current. So just like in the ideal model, a reverse bias diode still acts like an open switch, so no current flows in that situation. So good visual recap here. Uh, s- when the diode is forward biased, it acts like a closed switch plus the 0.7 volt drop across it, which is required to get it forward biased. When it's in reverse bias, it remains open. So this means the diode starts to conduct only after the source voltage exceeds that 0.7 volts, that barrier voltage. And why this matters? Because if your power supply is under 0.7 volts, nothing's going to happen. That's why real world circuits need to account for this drop, especially in low voltage designs or signal paths. So in a nutshell, the forward bias voltage is going to equal to 0.7 volts for silicon. The current through the resistor is going to be 0 amps because it still blocks in reverse bias. And the current is reduced by the forward drop, right? Again, this is getting us a little closer to reality than before. Um, yes. No, that's all. So it's time to bring real world diode behavior into focus. Last episode, we introduced the practical model. Now let's put it to the test with a classical example. So the circuit setup recap. We've got a 5-volt power supply, a 1 kilo ohm resistor, a diode in forward bias, and now we're using the practical model where the diode drops 0.7 volts. And so what are we finding? We're going to be calculating voltage across the diode, voltage across the resistor, current through the resistor. All right, so let's start off with step one, voltage across the diode. So in a practical model, we always assume a voltage drop across the diode in forward bias is 0.7 volts. So forward bias voltage, V sub F, is equal to 0.7 volts. Step two, voltage across the resistor. So now we just subtract the diode drop from the total voltage. If total voltage is 5 volts minus the 0.7 volts that's being dropped across the resistor, whatever remains has to be the voltage dropped through the resistor. So that's 4.3 volts. Now step three, current through the resistor. Again, going back to Ohm's law, current is equal to voltage divided by resistance. Now in this case, we have 4.3 volts, not that 5 volts we had before. So 4.3 volts divided by the 1 kilo ohm, that's going to give us 4.3 milliamps. Now to recap, voltage across the diode is 0.7 volts. Voltage across the resistor is 4.3 volts. And current through the circuit is 4.3 milliamps. That's lower than the 5 milliamps we got in the ideal model because now we're accounting for the real voltage drop of a silicon diode. Okay, you've seen the ideal model, explored the practical one, and now it's time for the real deal, the complete diode model. This is the most accurate way to represent a real diode in a circuit and what makes it complete. So this model goes beyond just the barrier potential. It also includes the forward dynamic resistance, which is denoted by R sub E prime, which is the resistance that the diode shows when it's conducting. Right? We also have a large reverse resistance, which is R sub R prime. That's the resistance when reverse biased, and it's usually very high, um, but it's not infinite. The forward bias behaviors in this particular model, the forward bias diode looks like a voltage source equal to 0.7 volts for silicon and in series with a small resistance R sub E prime that affects current flow at high currents. And this matters when you're working with fast switches, power electronics, or precision analog circuits. Now let's look at the same thing, but under reverse bias behavior now. So under reverse bias, the diode acts like an open switch, just like in the previous models, but there's still a tiny leakage current through a very large resistance, which is R sub R prime. So before we just assumed it was open, it was an infinite resistance, no current was actually going through. But the reality is, yes, there is a tiny leakage current that actually goes through the diode in reverse bias operation. So the resistance is so high that it's often ignored, but in sensitive circuits, it counts, right? So why use this complete model? It's the most accurate approximation of real diode behavior, and engineers use it when modeling fast switching or small signal diodes are in play. if you're trying to account for power loss, and let's say you're simulating exact behavior in analog circuits. So a quick recap for this slide is that barrier voltage, forward resistance, and reverse resistance have to be considered. Forward bias is going to be now equal to the forward bias voltage plus R times current, right? So the resistance RE prime times forward current, that's going to give us the total forward bias voltage. And then reverse bias is going to be equal to that large R sub R prime. And it ends up blocking current, but it, again, reality has a tiny leakage that goes through. And these are best used when you're working with detailed precision types of analysis, right? Okay, so in the last slide, we introduced the complete diode model, the most accurate way to simulate real diode behavior. Now let's walk through what that model looks like in action. So let's read the diagram together. In the forward bias condition, which is diagram A, so in this forward bias, the complete diode model shows the following: a voltage source V sub B, which is the barrier potential, which is about 0.7 volts for silicon. The series resistor R sub prime D, which represents the diode's dynamic forward resistance. I said R prime, R sub D prime, sorry. Okay, yeah. And then the closed switch to indicate that current is allowed to flow. And so what happens physically? So once your external voltage, that voltage bias is greater than VB, current flows. Unlike the ideal model, current is limited not only by your circuit resistor, but also by the diode's internal resistance at R sub D prime, or R prime sub D. I think that's what I said earlier. Now let's look at the figure B, the reverse bias condition. And you're going to see that you have an open switch, just like before, a very large reverse resistance shown as R sub R prime in parallel. So this accounts for the leakage current. And why show it this way? Well, because even though we say no current flows in reverse bias, there's always some leakage, especially in sensitive circuits or things with high voltages. This model makes sure that you don't forget that. So real circuit simulation accuracy is why you need this. And with this model, you can predict small drops in forward voltage as current increases. You can account for reverse leakage in precision or high-speed circuits. And then you can simulate diode temperature effects a little bit more reliably. And in a nutshell, in this slide, we said that forward bias is equal to the barrier voltage, V sub B, plus the series resistance, R sub D prime. Um, and then reverse bias is the open switch with large leakage resistance, the R sub R prime. And that's it. This is the most complete and useful model for real world engineering. Okay, we've explored the three major diode models, the ideal, the practical, and the complete. Now let's put them all side by side and see how they compare. So let's talk graphs. Each graph shows current on the vertical axis and voltage on the horizontal. They're broken into two regions, the forward bias when current is allowed to flow and reverse bias when current is blocked. So in the ideal model, the forward bias, as soon as the voltage is applied, current jumps straight up. There's no barrier or resistance. And with the ideal model of the reverse bias, you have zero current, no slope, it's pure block. It's perfect for quick calculations, but again, this is not realistic. In the practical model, you have that 0.7 volt threshold that appears before current flows. So once you pass that, current still rises sharply, and reverse bias still blocks current completely. But this adds some realism with the barrier potential, but it ignores internal resistance. Now, when we go to the complete model, here we see that it shows a 0.7 volt drop for forward conduction. Then the line slopes upward, not vertical. So this slope represents the diode's dynamic resistance. And in reverse bias, there's a tiny slope backward. That's leakage current due to high, but not infinite reverse resistance. So this model is the closest to how real diodes behave. Um, that is about it. Okay, up until now, we've been building your diode knowledge from the atom up, and now it's time to plug that knowledge into the wall, literally. So today we're starting our series on rectifiers. These are circuits that turn AC into DC using the one-way power of the diode. Why diodes work as rectifiers? Well, diodes conduct current in only one direction. That means when alternating current AC tries to reverse, like it does 50 or 60 times per second, the diode's going to say, not today. And this makes diodes perfect for rectifiers because circuits designed to convert AC voltage to DC voltage do it very well with a rectifier. Um, where else are rectifiers used? Well, to begin with, every power supply that charges your phone or powers your laptop uses a rectifier stage. So without it, you'd be pumping AC straight into your device, which it can't use, right? Your device uses, like your phone will probably use 5 volts at some amperage rating. But let's look at the types of rectifiers. We have a half-wave rectifier and a full-wave rectifier. So the half-wave rectifier only lets one half of the AC waveform through. This is a simple design, it's cheap, but it's not efficient when you're running it because it completely ignores the negative cycle or the other cycle. So a full wave rectifier lets both of the halves of the AC signal actually go through. It does it by flipping the negative half. Again, because you're utilizing both the positive and negative cycle, this ends up being more efficient. You'll have smoother power output. And a key point is that a diode's ability to block reverse current is what makes all of this possible. So no diode means no rectifier. No rectifier means no DC. So far, we've talked about diodes and rectifiers. Now it's time to connect the dots and walk through the full journey of power conversion inside what's called a DC power supply. So the problem, AC in and DC is needed. So almost everything in your home runs on AC power, alternating current. But like your phone, laptop, LED circuitry, they need DC or direct current. And that's where this power supply chain comes in. So let's go ahead and break this down. We start off with the transformer at step one, right? So we step down the voltage from the wall using a transformer. If the wall gives you 120 or 240 volts, the transformer lowers it to something safer like 12 volts AC. Right now at step two, this is the rectifier. The AC waveform passes through a rectifier, often built with diodes. Um, this turns that back and forth AC into one-way pulsating DC. It's still bumpy, but it's all positive. The next part is the filter. And so the filters smooth out those bumps, usually made with capacitors or inductors, and it turns the rough DC into a more stable voltage. So it's got ripples still, but not as bad as before. They're much smaller ripples and much cleaner. All right, the step four, which is the regulator, this stage locks in that final voltage. So whether you need 5 volts DC, 9 volts DC, 12 volts DC, even negative voltages, right? -5, -9, -12. This regulator ensures it stays constant even if your load or AC input changes. And then finally, it is the last part, which is the load. We deliver the clean, stable V out to the load, and your circuit, your charger, or your device delivers this. So to cap all this up, or recap, waveform evolution, we start off with AC in, which is sinusoidal. It's rectified, which looks like pulsed DC. Then we filter it, which looks like smoother DC, but with still some ripple. And then we regulate it, which looks more like a flat line, steady voltage. Right? And that's how you go from the wall socket to, let's say, your USB port. Now, putting a single diode to work in one of the simplest power circuits out there, and it's called the half-wave rectifier. So the basic idea is this. A half-wave rectifier uses one diode and the diode's key ability, which means it conducts current only in forward biased. Um, it blocks current when it's in the reverse bias operation. So that means that only one half of your AC input gets through, um, hence the name half-wave rectifier. Let's go ahead and break down the waveform. So here's what happens to the AC waveform. During the positive half cycle of the AC cycle, the diode is forward biased, current flows to the load, but during the negative half, the diode is reverse biased, so that means current is blocked, so nothing conducts on the reverse bias. And the output is a series of positive pulses, and this is your half wave DC. Looking at the circuit, if we look at the circuit like an overview, you've got an AC source, which is your voltage in. You have a single diode, it's in series, and a load resistor, which is what the diode's in series with, where the output voltage is going to appear. And the result is that every other half cycle of AC gets clipped. Now, there's pros and cons. The pro is that this is a simple design, it's inexpensive, it's great for low power or just learning applications. The cons, it's inefficient. We'll look at and we'll see why later. Right? You're throwing half of the waveform away. And the other con is that output is very bumpy and needs filtering for smooth DC. Okay, so we've talked about the half-wave rectifier, which was a simple way to convert AC into DC using just one diode. We're going to break down exactly how it operates step by step. So let's walk through the cycle. So the step one, the positive half cycle. When the input AC voltage Vin goes positive, the diode becomes forward biased. That means it starts conducting, and the current flows through the load resistor. And then what happens to V out? Well, the current produces an output voltage, V sub out, across the load that matches the shape of the positive half of that input AC sine wave. And that's how simple it is. On the negative half cycle, though, here's where the magic begins. So when Vin goes negative, the diode becomes reverse bias. So it's shutting it off like a switch just opening. All right, so it's blocking current from flowing. So you get no output. No current flows, there's no voltage drop across the load, and the output drops to zero for this half of the wave. And the final output waveform, well, the result, it's going to be a pulsating waveform at the output. Voltage during the positive half cycle, um, flat zero during the negative half cycle, and what else? That's it. And this is your classic half wave DC. So let's recap this whole slide so that the diode turns on during the positive input, diode turns off during the negative input, and output mimics only the positive half cycle of the AC input. All right, let's talk about the half wave rectifier, negative half cycle, and reverse. So we're going to talk about closing out the operation of half wave rectifier, and then a bit of a tease for a challenge here. So again, we saw how a diode acts as a gatekeeper in a half wave rectifier, letting through the positive half of the AC waveform and blocking the negative. We're going to zoom in on what happens during the second half of the wave and what flips if we flip the diode, right? What happens if we flip the diode? So let's talk about that. The negative half cycle in operation. When the AC input goes negative, the diode becomes reverse bias. What does that mean? That means that no current will flow, the diode shuts off, and the load resistor gets nothing. The result at the output, V sub out. So during this negative cycle, the output voltage is zero. So you're left with just the positive half cycle, creating what we call the pulsating DC. And then the average output, well, the average value of the pulsating voltage is going to be V average time being equal to V peak divided by pi. So it's lower than the peak, but it gives us a usable DC level. Now here's where the twist comes in. If the diode were to be reversed, in other words, we just change the direction. What happens if we do that? Well, the circuit still works exactly the same, but in reverse. So now the diode is forward biased during the negative half cycle, and it blocks the positive half if we were to reverse that diode. All right, so the output becomes inverted. It's made of negative pulses in this case instead of the positive ones. You get the same concept, but the the polarity is flipped. We've seen how half-wave rectifiers work in theory, but let's add a little reality to the mix, specifically that 0.7 volt reality check, if you remember. So the focus here is going to be the effect of the barrier potential on your output voltage. So again, what was the barrier potential? In a practical diode, especially silicon-based ones, there is a built-in voltage drop, and this energy, what it is the energy that needs to be overcome so that depletion region can be overcome and diode will turn on. And that voltage drop is about 0.7 volts. What does this mean for rectifiers? So during the positive half cycle of the AC input, the voltage needs to be at least 0.7 volts before the diode conducts. So that means that your output peak is always lower than the input peak. So a simple equation is that V sub P out is going to be equal to V sub P in minus the 0.7 volts. So if your input peaks at 10 volts, your output peaks at 9.3 volts, just because we lost that 0.7. The diode eats at 0.7 every time it turns on. And this matters because in low voltage circuits, that drop, it can be significant. Right? If you're dealing with large voltage, 0.7 volts is not very much. But if you're dealing with low voltage circuits, yeah, 0.7 volts could definitely make the difference. So if your input is only, let's say, 1 volt, you're losing 70% of it. So in a regulated DC supply, you have to design around this particular drop, this 0.7 volt drop. Always account for it, whether you're building a rectifier, a clipper, or a limiter, and we'll find out what those types of circuits are next. Always factor in that V sub F drop for your results, right? Or else they're going to be off. Hey listeners, welcome back to Circuit Chats in our journey through rectifiers and diode circuits. So it's time we talk about something that doesn't just make your circuit work. It keeps your circuit from blowing up. And that's the topic of what's called peak inverse voltage, or PIV for short. So what is PIV? It's the maximum voltage a diode can block when it's reverse biased without breaking down. In other words, without the material itself just degrading. So we call it the peak reverse voltage as well. It's that it's super critical in circuits like rectifier circuits. And when does this matter? So in a half-wave rectifier, for example, during the negative half cycle, the diode is reverse biased. And so at that point, it sees the full peak of the input for the AC voltage that's trying to push through that component. So the P sub IV is going to be equal to P sub P, right? V sub P, which is the peak input voltage, but in the negative direction. Now, if your AC input peaks, let's say at 20 volts, your diode better be able to block at least 20 volts in reverse, right? So if you got a diode or a component that can't handle that voltage and your reverse bias voltage is much higher, you're going to physically deteriorate, burn the component. So there's a safety rule that engineers use. So we don't normally ever make it that close. We use a following safety margin. So if a diode is rated, needs to be rated at least 20% higher than what that peak inverse voltage is. So for a 20 volt peak, we'd want something or a diode that was rated to be greater than or equal to 24 volts, right? So something a little bit higher than that peak in case you get some surges and yeah, so it just buys you a little more safety, a little cushion there, a little buffer. If the diode, if the diode isn't not rated high enough for the circuit that it will be working in, when it goes into reverse voltage, it's just basically going to punch through the component, through the material, and it's physically going to destroy the component. So the diode, in other words, it starts breaking down, it goes into overvoltage, and it just fries, it crisps. Right? So let's recap what we talked about on this slide. Peak inverse voltage. It's the most amount of reverse voltage across the diode, peak reverse voltage, right? And that happens when the diode is in the off position, not off position, but when it's off, meaning that it's blocking the reverse cycle. And that's it. Always choose a diode with a rating 1.2 times higher than the voltage peak. Okay, before your diode can turn AC into DC, the power has to be shaped, sized, and safely delivered. And for that, we bring in the transformer. the unsung hero of everyday power supplies. So let's talk about transformer coupling first and what it is. So transformer coupling means using a transformer to connect the AC input to the rectifier, right? So it doesn't just pass the power, it modifies it and it protects your circuit. So it's got two big jobs. First, it can either step up or step down the voltage. And second, it provides electrical isolation. So for step up and step down, that depends on your circuit needs. A transformer can either reduce or increase the AC voltage. That way your diodes and components only see what they can handle. And then where electrical isolation is concerned, there's no direct wire connection between the primary, which is the input, and the secondary, which is the output. So because you have no physical direct wire, this protects the rest of the circuit from surges or faults in the power line. Another important concept to understand is the turns ratio when we're talking about transformers. So the transformers effect is determined by its turns ratio, and that just means how many wire loops are on the primary versus the secondary side of the coil. And so you can see here from the slide where we have n being equal to the equal to the turns ratio, sorry, which is equal to the number of turns on the secondary side divided by the number of turns on the primary side. And then we can also use this to determine the voltage based on that ratio. So voltage on the secondary side would be equal to that ratio of turns on the secondary over the turns on the primary times the voltage on the primary, and that should give us the voltage that's on the secondary. So if the secondary has half the windings of the primary, you get half the voltage. So for example, you had let's say you had 120 volts coming in. Let's say you had a 10-to-1 step down. So you had a 10 turns on the primary for every 1 turn on the secondary. So we're dropping it down by 10-to-1. And so that means on the secondary, we would get 12 volts out, 12 volts AC out. Right? And so that seems a whole lot better instead of 120 all the way down to 12 to feed a diode, so you won't burn out a diode. Okay, so let's move on to the next slide. Okay, so far we've talked about diodes, rectifiers, and transformers on their own, and now we're putting them together in one of the most common real-world circuits, which is the transformer-coupled half-wave rectifier. So let's look at and see what's happening here in this particular setup. So we have AC voltage that comes in from the line, it goes into the transformer. Now the transformer, it's either going to step up the voltage or step it down as needed. On the secondary winding of the transformer, that connects to a diode, which performs half-wave rectification. The diode sends current through a load resistor only during that positive half cycle. So let's do some quick math real quick to look at the output peak voltage. So you won't get the full secondary voltage on the output. And the reason is because the diode's barrier potential voltage eats up a little bit of that. So remember that 0.7 volts. So VP out is going to be equal to voltage on the secondary minus that 0.7 volts. Now let's talk about that was the output peak voltage. Let's look at the peak inverse voltage. So during the negative half cycle of this waveform, the diode is in reverse bias. It has to block the full secondary voltage. So the peak inverse voltage is going to be equal to voltage on the secondary. A recap, or at least a reminder, always pick a diode that has 20% higher PIV rating than what you're using, than the maximum that you're using. That's it. Remember why we use transformers. They can step down or step up voltage. They can electrically isolate the source from the circuit, and they make the peak inverse voltage and output voltages more predictable. So today we are solving a real world example. So a transformer coupled half-wave rectifier circuit. So get your calculator. We're going to work through these calculations. We're going to learn how to work or calculate peak output voltage and the peak inverse rating for the diode. So what do they give us? They give us that the primary voltage is equal to 100 volts peak. They give us a turns ratio of 2-to-1. That means that the secondary voltage will be half the primary. Remember, the primary has 2 windings for every 1 winding on the secondary side. So the voltage is being dropped here. All right, so that means that the voltage secondary is going to be equal to voltage primary divided by 2, which is going to, in this case, going to be equal to 100 divided by 2, which is 50 volts. Okay, now let's look at the peak output voltage. So we can apply the voltages, the diode's variable potential to this secondary. So remember that's going to be 0.7 volts. So VP out will be equal to V sub secondary minus the 0.7 volts. And so we plug in the numbers. We have 50 volts minus 0.7 volts. That'll give us 49.3 volts. And that'll be what we should be expecting for peak output voltage. Now for peak inverse voltage rating for the diode, it says during the reverse half cycle, the diode sees the full um, peak inverse during that reverse cycle, so when it's reverse bias. So voltage on the secondary is going to be equal to the peak inverse voltage. So in this case, it'll be 50 volts, right? So again, remember to add 20% to that 50 volts. So we multiply 50 volts times 1.2, and that's going to give us a rating of 60. So we want a diode, for, in this case, to handle a peak inverse volt rating of 60 volts if our peak is going to be 50 volts. And that's it. That's it for this example. I want to thank you very much for your time, and I will see you in the next podcast, next lecture.